At this stage, you should be able to recognize a feature control frame in a design specification and correspond that to a specific part feature. As you recall, as part of that feature control frame, there is a description of the size of the tolerance zone. We'll look at that today, and then we'll start into some shape tolerances and show that relationship. The first concept that we'll look at is this notion of a static geometric tolerance. And obviously, by using the term static, we mean that there's no change in that specification. And that's versus this idea of a dynamic tolerance, which is sometimes referred to as a bonus tolerance. And that will change depending upon the part dimensions. So there's going to be this relationship to dimensional characteristics and the geometric tolerance in some cases, not in all cases. We'll also show some of the effects of the material condition. As you know, you might want to go back and review that. Maximum material condition and least material condition are two special conditions based on the dimensional tolerance. And then we'll talk about some tolerance zone effects. Well, the simplest case would be the static tolerance, and here there are no material conditions. So we can see in this second box of the feature control frame here that we have a description of the size of the tolerance zone. This is the actual tolerance zone here. You can see it's a perfect geometry. Remember, tolerance zones are concepts only. They don't actually exist. Now, when you see this diameter symbol in that second box, that's a hint that you're dealing with a cylindrical tolerance zone shape in most cases. In some cases, it'll be a spherical shape, and we'll look at those special cases. But primarily, it will be a cylindrical shape. And then the width of the tolerance zone is fixed at 0.05, as you can see here. And I say width because the meaning of the width will vary depending on the shape. So in this case, obviously the width corresponds to the diameter of the tolerance zone. Note, by static, we're saying we have a constant value for the size of the tolerance zone. What about a dynamic tolerance? Whenever you have a dynamic tolerance, what you're going to see is the use of material condition in that size specification at a minimum, and we'll see some variations on that later on. What this will do is increase the size of the tolerance zone as we deviate from material condition. So you have to know the material condition, and you have to know the deviation from that material condition. The interesting thing about the dynamic tolerance is the actual size is unknown until we actually make a part. And therefore you can think of the size of this tolerance zone as being unique for each part, because each part will have its own unique deviation and therefore its own unique size for the tolerance zone. Only the upper and lower bounds of the zone size can be determined from the design spec. So we can find these boundaries, but we don't know the actual until we make our part. Note again this distinction here. We measure deviations and we specify tolerances. We don't measure tolerances. Well, how do you know you have material condition in your specification? The material conditions will appear primarily as an M, meaning maximum material condition, M in the circle, or L in the circle, least material condition. And I would venture to guess about 99% of what you're going to see is this maximum material condition, and there's a reason for that that we'll see later on. When you see that material condition, What you're saying is the dimension of the feature that maximizes the amount of material versus least material condition, that would be the opposite end, the dimension that minimizes the amount of material on the feature. Now be careful here, because if I have an internal feature such as a hole or blind hole, that will have a different meaning than if I have an external feature such as a protrusion. So you better know what feature you're talking about. That will affect which dimension you use to determine the material condition. If you don't see an M or an L, then that says regardless of feature size, and there's no relationship between the size of the feature and tolerance. In other words, this is the default, this is the static condition. But if I see an M or an L, that means I'm going to have a dynamic tolerance. That's okay. So you should be able to identify the maximum material condition and least material condition for any part feature based on the dimensional tolerance. Let's look at an example here. We have a cylindrical feature, and the question is, what is the MMC condition for this part feature? So we look at the dimensional tolerance, and we see that since we have solid material here, MMC would correspond to the largest dimension in this limit tolerance, and so our maximum material condition would be 1.30, indicated by the diameter of this dotted circle. You should be able to do the same thing for least material condition as well. Now, what is the effect on the tolerance zone in that example? Well, you can see when the actual diameter, and again, don't forget, you don't know the tolerance zone width if you have a dynamic tolerance until you measure the actual part after manufacturing. What if we measure it and it's 1.30 for that example? Then that means the width of the tolerance zone, and here's our tolerance zone here, would correspond to our static portion, 0.01, plus the deviation from maximum material condition, 1.3. Well, you can see obviously there is no deviation, and therefore that's the smallest our tolerance zone can be. And then if we make a part and we measure its diameter and it turns out to be 1.25, then we're going to say that the width of the tolerance zone corresponds to the static part plus the dynamic portion, which now is significant, up to 0.06, so 6 times the width at MMC. So we're allowing greater deviation in the geometry as we depart from maximum material condition. Well, in general, if we look at the material condition, specifically in this case maximum material condition, what we said we're going to do is, first of all, measure the part feature. So whatever that feature is, after we make it, we measure it, find the deviation from the material condition, and then add that deviation as the dynamic part of the total tolerance, and this is what we're adding. What happens when this changes to L? Then we just replace this with LMC. Well, that was the effect on the tolerance zone size. What about the effect on the surface of the feature that we just created? In order to evaluate that, we're going to define something that we call virtual condition, and the virtual condition will correspond to the boundary of the material condition that incorporates the tolerance zone size, because if our tolerance zone allows deviation, then that means the surface itself will be allowed to deviate. So we're going to look at this notion of a worst case scenario for virtual condition, where we take, in this case, our maximum material condition, 1.30, and we allow a deviation from maximum material condition, which we found to be 0 when our part is at maximum material condition. And then we'll add whatever tolerance zone width we have to see where the surface is going to be. So now this red circle indicates this extreme boundary, and all parts must lie within that boundary in terms of their surface. So in general, if we look at the worst case scenarios for our virtual condition, we're going to see 2 types of specifications. Again, this will be by far the most common one you'll see. And so in that example, we could add in that size of the tolerance zone, T, or we could subtract it. Now we had solid material, so we added it, but if it was a hole, then we're going to subtract it because that surface, the interior of the hole, is allowed to vary, and so we have to find essentially the smallest hole that would be the boundary for every hole on every part that we make. So that's virtual condition. The opposite of virtual condition, because we would obviously have to have another boundary within which the surface lies, is what we call the resultant condition. And here we're going to take, again, the extreme boundary, but it'll be the complement of the virtual condition. When M is specified, we could think of it as we've got solid material for an external feature. And so similar to what we did with virtual condition, we'll look at the opposite end, LMC, for a hole, also LMC. But now, instead of just T, the static part, we have to add in the dynamic portion as well. So we take the maximum difference between MMC and LMC, add that into our static T, and then for an external hole, it will be our external feature, it will be minus. For a internal feature or hole, it will be plus. And then it's just the opposite if you happen to see an L. But again, most of what you're going to deal with will be here. Okay, so how does that play out? Let's look at an example where we have our virtual condition and resultant condition for this external feature. And now we can see this hasn't changed for our external feature, but now we've got this resultant condition that's made up of the static part and then this part is the dynamic part. So you can see it's significantly less than 1.25. So what we're saying here is our surface is going to lie between 1.19 and 1.31. Over here, what does that mean? Well, you can see between the red region and green region, we potentially have some voids, right? Empty space due to deviations. But in the green region here, this is all solid material. So we've got our boundary cases, inner and outer boundaries, based upon whether it's maximum material condition or least material condition. Again, typically you're going to see the maximum material condition used in most cases. So primarily we'll be concerned about this, but you might see this in a few cases. Well, the example that we did was the outer and inner in the previous case. And then that just reverses if you're going to do a hole feature. The virtual becomes the inner boundary, the resultant becomes the outer boundary. Again, what we're describing is a region in which the surface must lie if we take the two into consideration, both resultant and virtual condition. So at this point you should understand static tolerance zone size. That's just the numerical constant you see in the second box. The dynamic tolerance zone, think of this as being based upon a material condition, M or L. And then virtual condition and its relationship to resultant condition, describing two surfaces between which your actual surface will lie. Tolerance zone using material condition, again, unknown. If you need to find that material condition, you'll have to measure it and determine the deviations from that material condition for all your features. Once you do that, then you add the deviations to the static portion, and you can think of your inner and outer surface boundaries being affected by that tolerance zone size. In other words, they will shrink or expand depending on how large that tolerance is. So let's look at example of shape tolerances. The simple ones are straightness and flatness. and we've already looked a little bit at straightness. We'll also look at the role of material condition in the specifications. Now, there are many different combinations of material conditions and the type of tolerance zones. You have to know what is possible and what is not possible. Some will be obvious and others may not, but I'll point that out as we go through these. Okay, what is straightness form tolerance? We're thinking of our resultant geometry and essentially how straight is it. So we may have many features in which we could describe them as being straight. The question is, what does it correspond to? Because that will affect whether we have a 2D or 3D tolerance zone dimensionality. If it's 2D, you can think of it as two parallel lines or a rectangle. If it's 3D, we're going to think of cylindrical type tolerance zone, and then we'll have a special case. There are no predefined location or orientation. Now this is very important. If you go back to the table from the last lecture, you'll note that we don't care about the orientation of the surface. We don't care how it's positioned. All we care about is whether it's straight or not. So this is the simplest form that we'll see, the symbol followed by a value and perhaps material condition. If we look at a surface, and here we can see that I've got a leader line connected to a surface. When we do that, what we're saying is this tolerance corresponds to the surface straightness, and we'll take cross sections of the surface. As you can see here, we're essentially going in this direction and running our straightness tolerance zone across each one. Each one is independent, and note, you can't use material condition on this surface. And that makes sense because what would we use as our material condition? So it's kind of like in 248 when you did surface roughness, you may have taken a scribe across the surface and determined how rough that surface is. Well, we're on a much larger scale here, but if we magnify that, this is what we're seeing, deviations in the surface, and they have to fall within our rectangle or two parallel lines separated by that constant value. Note that each cross-section is independent. So when I say cross-section, as we cut through this surface, we're saying that each one is independent. There's no connection between them. The straightness of a midplane is a special case, and note this designation that we have for the leader line, and we'll emphasize this again later on. We're attaching it to the dimension line. This is very important. So it depends upon the attachment point as to the meaning of this tolerance. If it was not attached to the dimension line, then we're talking about this surface here. But since it is, then we're talking about this imaginary midplane for protrusion or slot. So if we look at it from the end, what we're saying is we're looking at a midplane and making sure that it's straight. Now in this case, it's a special case where we have a 3D zone of two parallel planes, again separated by 0.025. Material condition can be used in this case, so that's a special case. Note what's happening here. If I control the midplane, and that's what's indicated by this gray region here, so as this particular part distorts or bends and the midplane distorts, as long as it's contained between those two planes, we're indirectly controlling the surfaces. So by controlling the midplane indirectly, you're controlling the surfaces themselves. Well, what happens when we have a material condition? As we've already seen, we'll have to take into account the fact that we've got a material condition here, and in this case MMC. So we have to look at the largest dimension because that will maximize this solid region, and then add in, here's the largest dimension, add in the static plus measure the actual height dimensionally of this. Once we do that, then we'll know what the width of this tolerance zone is. Again, the meaning is still the same. Two parallel planes, that represents the shape of the tolerance zone, and the midplane must lie between those. Okay, this is a common use of straightness when we want to control how straight an axis is. And immediately you should recognize that because we have this diameter symbol, it indicates that we have a cylindrical tolerance zone. So the entire axis must lie within a cylinder of diameter t. Note that material condition can't be used because, again, this diameter could vary. Note the attachment here. I've got an attachment of the feature control frame directly to the dimension line. Now that's not the only way it can be specified. We could have an attachment to the circumference here, and that would have the same meaning. Again, indirectly, because you're controlling the axis, you're also controlling the surface shape. So the amount to which this surface can be extended beyond a cylinder. And as you can see down here, we've got our cylindrically shaped tolerance zone indicated by the shaded region. It has a fixed width because there's no material condition, and the axis has to fit completely within that tolerance zone. Note we're not worried about orientation or position, so that can move anywhere in space. Now we can add material condition as we did before, and that's indicated by the M here in the size part of the frame. So we add in the maximum the difference between maximum material condition and actual, which means I have to, when I make this, I have to measure the diameter of the cylinder. And now we've got this additional tolerance. We don't know what it is until we actually make it. But the principle is still the same. The zone has to contain the geometry. In this case, the geometry is the axis because of this diameter symbol that we've identified here. Okay, flatness. This is a pretty simple concept here. If you understand straightness, we'll directly control the entire surface. By doing that, we will define a 3D tolerance zone by taking two parallel planes. Another way you can look at this is think of it as putting a box, a virtual box, around a surface. Note that there's no predefined location or orientation. It can be anywhere in space. And this is important, material condition cannot be used. Okay? So if you see an M here, that's a mistake, right? So you shouldn't see any material condition in a flatness specification. You should just see a symbol and the width of the tolerance zone. Obviously, it'll be static. Well, how do we specify the flatness of the surface? Again, we have to attach it with some mechanism. In this case, it's a simple leader pushing or pointing to the top surface. And we have two parallel planes representing our box. Note I put these at an angle just to indicate that I'm not concerned about the orientation of the surface. It can have any orientation as long as the entire surface lies between these two red planes separated by a distance of 0.05. Okay, so you should understand how the straightness tolerance can be used on a surface or a derived geometry, such as, by derived geometry, I mean an axis would be an example, or the midplane. And we also saw in some cases we would have a material condition when we have a feature of size. We also can control using the flatness, shape tolerance, flatness of an entire surface. Straightness controls surfaces directly and indirectly. By controlling an axis, we're controlling surfaces. Flatness, however, controls the surface directly. And mature condition can only be used in straightness specifications for an axis or midplane. So please note when you can use material condition and when that is not allowable.